The last part that we're going to talk about is section 9.7, and it's talking about circles and lengths of segments. Now, some of these theorems sound quite wordy, but the actual math in them is not hard. So theorem 9.11 says that when two chords intersect in a circle, we have chord DB and AC intersecting. It says when they intersect, then the product of the segments of one chord equals the product of the segments of the other chord. Well, first you need to know that product means when two things are multiplied by each other. So that answer would be the product. So they're saying that if we take DB and it intersects AC, then these two pieces of DB multiplied together should equal these two pieces of the other chord. So DB has two pieces. From D until the center is equals 2, and then from here to the end equals 6. So this theorem says that 2 times 6 should equal the product of the two pieces of the other chord that intersects it. So this other chord has 3 and 4. So 3 times 4. So 12 does equal 12. So that's all that theorem 9.11 says. That if you have two chords that intersect, then the product of the pieces of one chord has to equal the product of the pieces of the other. So we'll do some examples that work with that theorem in a second, but I want to show you theorem 9.12. Theorem 9.12 is similar, only this time instead of chords we have two secants. Remember that a secant forms an angle outside of the circle. So then it becomes something different. In this case, the product of this whole sequent times the outside part should equal the product of this whole secant times its outside part. So it's different from the chords. In the chords, we're multiplying the two pieces together. So that's why it would be 2 times 6 and then 3 times 4. But in a secant, the product is of the whole thing times the outside part and this whole one times this outside part. So in this diagram, this entire secant, C to P, equals 12. So this whole segment right here equals 12. And then the outside part of it equals 5. They also tell us that the entire secant here, A to P, equals 10, and this outside piece is 6. This theorem states then that this entire piece of the sequent, which is 12, if you multiply it by its external segment, which is 5, it should equal this whole sequent, which is 10, multiplied by its outside segment, which is 6. 12 times 5 is 60, right? And 10 times 6 is also 60. So they equal. So we'll be able to use this theorem to figure out parts of the circle as well. There's only one more theorem to learn this week, and that's theorem 9.13. 9.13 is related to those other two that we just talked about. But here we have a circle, and we have a tangent segment, so it just touches in one spot, and then we have a secant, which is a chord that is extended and meets outside of the circle. So here, this theorem says that when a secant segment, this one, and a tangent segment are drawn to a circle from an external point, here's my external point, then the product of the whole secant, just like last time, the product of this whole secant times the product of its external segment has to equal this tangent segment times itself, or the tangent squared. So what does that mean? That means if this tangent is 8, let's call that 8, from here where it meets to here. And let's say that this whole segment right here, from, I should give these some letters, we'll call that A. From A until P is, I should have worked out the numbers beforehand. Let me think for a second. Let's say that it's 16. Let's say that it's 16. From A till P is 16. And then this external part, just from C till P, is going to be 4. So this theorem says that the external secant the entire piece of it, which would be 16, multiplied by its external one, 4, should be equal to signs. So our answer would be -6 times -2. That equals a positive 12, but a -8 when you add them together. So I would say this parentheses would be x minus 6, and in this one would be x minus 2. So the answer to this problem is actually, you have two different answers. You have to look and see what makes this parentheses equal to 0. So x minus 6 equals 0. In order for x to be 0, then x in this case has to be 6. But we also need to look at this set of parentheses and see, when does x minus 2 equal 0? X minus 2 equals 0 when x is 2. So this problem actually has two answers. X could be 6 or x could be 2. And you need both of those answers for it to be correct. I think that's all that I'm going to go over for this chapter. That's all that there is. But please don't hesitate to contact me if you are confused about anything. Good luck.